Do you remember when was the first time you used a computer?
Sure, when I was an undergrad at Amherst College, and we used the IBM 360 with paper job cards, and to debug the code, there were these massive books with every line of code that you'd open on the floor and get down there and try to figure out what went wrong.
What year?
Maybe 76, something like that. And I always loved computers. I always liked the idea that in the final analysis, you can get them to do what you want. They're mulish, they're literal. But in the final analysis, you can get them to do whatever you need. I don't think the computer is the main thing. It facilitates a change in epistemology and a change in application. But I think the main move is the conceptual move, is what do you mean by an explanation in the social sciences? And if you mean that I need to generate the thing from a population of cognitively plausible interacting agents, then that's a different game. One day, after everyone had finished lunch in the Brookings cafeteria, we stayed after, and on napkins in the Brookings cafeteria, tried to sketch out the simplest possible society we could model computationally. That was how it got started, and we made, I thought, very felicitous choices. And I have the original program, Rob Axtell and Josh Epstein, Hunters, 1991 or something. At that time, it was just, look, let's think there's some resource landscape, and we have hunters and gatherers on the landscape who look around, look for better sites, go to the better site, harvest the resource, have a metabolism, have some vision of really primitive specification. It turned out to go everywhere. We, of course, used the model to study spatial segregation into tribes, trade, violence, combat, cultural transmission. It remains, I think, the only really unified immunoepidemiology model where there are immune systems evolving and they affect how contagious you are and so forth. And the idea was, let's try to build a full-up evolutionary social science, where there's a lot going on and society's a high-dimensional thing with movement and migration and trade and combat and disease. Since Rob and I did the Sugarscape work, the computing is just unrecognizable. And the computing power itself, you just couldn't, this was, 500 agents. And we thought, whoa, that is some serious large-scale modeling. Now it's just unbelievable. There are these huge economic models, huge epidemic models, huge transportation models. These things were just not even imaginable when we first started out. And also the cognitive depth of the agents is now possible. And I think that trade-off between model size and individual agent complexity is a lot less severe than it was then. There were no specialized agent-based modeling programs, there were no courses, there were no textbooks, there was nothing. We were really flying blind. I think the first version of the hunter-gatherer code was in regular native Pascal. Object-oriented Pascal didn't even exist. Rob figured out how to do doubly linked lists, and I learned how to do that, and we wrote all this very, very fancy code with pointers to pointers and handles and all this deep stuff. It was just the Wild West. It was really the Wild West. Everybody did whatever the heck you had to do to get the thing to work, and there were no standards, there were no, none of that. Languages were all over the place. Now it's a whole other story, right? Now there's there's Repass and NetLogo and Mason and all these other Python, a million ways to do agent-based modeling. The programming languages have gotten much better than what we had.
What would you say it's better? Why?
With their unified development, their integrated development environments. Mm-hmm. An environment like NetLogo, and it's got onboard visualization, onboard statistical distributions. I say I want you to develop a network that has exponential degree distribution with mean 5. Bam, no problem. Got the visualization there. You can select. Visualization when we did this book was also incredibly primitive. Yeah. It's unbelievable. It was a mess. Res edit, all these Mac toolbox, all this horrible code, wait next event, button down, all these There's a lot on the cutting room floor, a huge amount on the cutting room floor, that didn't work out, or you got some off by one thing, or you did the network wrong, or this should have been an out, a two-way link, and it's really a one-way link. I mean, all kinds of gnarly little crud all the time. I mean, that's life in computational modeling. For me, that's life in the trenches, writing code. And all that's been removed. I mean, it's just very smooth and easy to do. The low-level, yucky programming has been swept away. Computing has facilitated the advance of this science. Object-oriented programming was exactly right for agent-based modeling. And it was a real boom.
Can you elaborate on the reason why object-oriented was a game changer?
It simply accorded with the concept of an agent in a very straightforward way. Agents have methods, they have instance variables. It was natural to bundle them together as objects and then have the objects interact in the code and evolve and affect one another and update one another and do all the things we're interested in, form networks, dissolve them, etc. But using computers is not the point. You can use computers to do very traditional economics, and there are a lot of economists using traditional computing to take the traditional representative agent macro. That's irrelevant. What's relevant is what is the explanatory standard? What is the scientific instrument in constructing explanations meeting that standard? And it turns out the computing has developed to the point where this is a serious alternative way of doing social science, including economics.